We are diving deep into the place where cutting-edge, blazing fast AI coding meets the uh, grimy, essential world of fundamental cybersecurity. We're talking about the software supply chain.
And it's a collision that's happening right now on basically every developer's machine.
For anyone building software today, especially those of us, living in the modern development environment, we've all felt the seduction.
Yeah.
It's what our sources analyzing this trend have perfectly named vibe coding.
It's a great term. It really captures the feeling. It's less about engineering and more about, well, a vibe.
Exactly. I mean, think about your workflow now versus just, 2 years ago.
Oh, it's night day.
You've got your AI agents, whether you're using something like Cursor or Replit or, whatever flavor of enhanced IDE you've chosen. And they aren't just giving you slightly better autocomplete suggestions anymore.
Not at all. We're talking about building entire complex features with just a couple of natural language prompts.
And you, the developer, you've been elevated from hands-on keyboard coder to the high-level supervisor.
Right. You're just sort of sitting back, occasionally nodding, maybe tweaking a doc string here and there.
But the heavy lifting, the boilerplate, the dependency search, that's all automated. It feels incredibly fast.
It feels like magic.
But that speed, that frictionless flow, is exactly the problem, and it's created a catastrophic security blind spot.
Mm-hmm. The source material puts it pretty bluntly.
It does. It says letting AI agents blindly pull in dependencies is playing Russian roulette with the global software supply chain.
And that's not an exaggeration. We're talking about an existential risk that's amplified by the very tools we think are helping us.
And we don't have to guess about the danger.
Yeah.
The immediate context for this dive is a recent, very specific wave of hacks that proved this theory almost instantly.
The cursor hacks.
We are talking about malicious NPM packages that were masquerading as official Cursor APIs. These packages targeted those AI-driven IDEs directly.
And the kicker is, because these malicious packages were suggested by the very agent the developer trusted, they just sailed right past all normal human scrutiny.
That trust was the vulnerability.
It was the entire attack vector.
So our mission today is clear. We need to understand this structural failure at its core, why AI speed inherently breaks our traditional security models.
Right, and then we need to trace the specific modern attack vectors that exploit the trust we place in these AI tools.
And most importantly, we need to identify the specific battle-tested tools, the automated defense stack. We need to regain control and rigorously verify the code entering our systems.
And crucially, do all of that without sacrificing that fantastic velocity that AI gives us. Because stopping the AI, that's not an option.
Securing it is.
And that framework securing velocity, not stopping it, is really the only way forward. The fundamental shift here, which the analysis emphasizes, is recognizing the scope of the AI's actions.
What do you mean by scope?
Well, when an AI agent vibes its way through a build, it doesn't just write code, it imports it. It pulls from this vast, chaotic, and largely unregulated ocean of open source registries.
PyPI, NPM, Maven Central, Docker Hub, all of it.
All of it. And that distinction writing code versus importing unvetted packages feels like the core of the problem.
It is. It is the core.
It is. And this brings us directly to what the source material correctly identifies as the bypassing of human hesitation.
Human hesitation. That's an interesting phrase.
The AI agent, by its very nature, its singular focus on solving the task you gave it, bypasses the most critical security filter in history: human hesitation.
Okay, unpack that for me. What does that hesitation look like in the, let's say, the pre-AI world?
Okay, think back to even just a couple years ago. When you as a human developer were going to use a brand new library or a new vendor, what did you do?
I'd Google it, check the GitHub repo, see how many stars it has.
Exactly. You applied natural skeptical friction. You might check the repository's history, look at the last commit date, read the licensing.
Or I'd just ask a senior dev on Slack, hey, have you used this thing before? Is it legit?
Yes. That question right there, have you used this before? That process, that moment of pause, is the critical security bottleneck that has saved countless projects from disaster.
But now, when an LLM is integrated directly into my development environment, it's an internal utility, a trusted part of the fabric.
Right.
And it suggests, hey, to implement this feature, I need this dependency, and here is the precise command to install it. That friction just... it evaporates.
It disappears completely. The developer trusts the agent, they trust the efficiency, they see a solution to their problem presented with the confidence of an oracle.
So you don't switch context. You don't open a browser and search the registry for verification.
You just execute the installation command. The AI effectively imports third-party code, bypassing all the scrutiny a human would typically apply to a new vendor or a suspicious-looking package name.
That is a fundamental breakdown. It flips the security model from, I trust this code because I vetted the source.
True. I trust this code because my trusted AI suggested it.
It assumes security is baked into the suggestion process itself.
Which is clearly demonstrably false. And the scale of our reliance on imported code makes this breakdown catastrophic. We have to talk about the 80-90 rule.
The iceberg of code.
The iceberg of code. This is the foundational supply chain reality that many developers, especially those deep into vibe coding, simply forget.
And the rule is what? 80 to 90% of the code isn't yours?
Exactly. In modern application development, 80 to 90% of the resulting code base is not code written by the developer or generated by the agent. It is third-party open source code pulled from these public registries.
So the developer who is vibe coding is looking at that 10% of code the AI just generated for them, the new function, the API wrapper, that small logic block.
And they focus their risk assessment right there. They look at that surface snippet and say, okay, that looks fine, logic's correct.
They are focused entirely on the tip of the iceberg, the code they can see above the waterline.
Correct. The visible layer is the 10%. But the real risk, the structural risk, the unvetted, unscrutinized code that is responsible for 90% of your application's surface area, that lies in the dependencies beneath the surface.
It's the transitive dependencies.
It's the transitive dependencies, the libraries that those libraries rely on, and the scripts that execute the moment you install them.
So wait, if 90% of our code is third-party, and we're now using an overly confident, friction-free AI to select those third parties for us, isn't the problem bigger than just a piece of malware?
It is.
It sounds like we've introduced structural instability into the entire software assembly process.
That is exactly what it is. This is not just a localized malware problem. The fact that a developer's implicit trust in their AI tool can be so easily weaponized to pull in a poisoned package, that demonstrates a deep structural failure in how we assemble software today.
We've basically outsourced the vast majority of our code base to an unregulated public market.
And now we are, in effect, outsourcing the vetting and the selection of that code to an AI that is rewarded for speed, not for skepticism.
It's just performing a statistical prediction.
That's all it is. It's saying, based on my training data of billions of lines of code, this is the most likely package name for this function. And that statistical prediction has created a perfect exploitable target.
Okay, so let's unpack this. Let's zero in on the specific attack vectors. This isn't just general carelessness anymore. This is about highly targeted structural attacks on the development process itself, weaponizing the very intelligence of the LLM.
It is. And the most elegant and insidious vector relies entirely on exploiting the nature of large language models themselves.
Which brings us to vector one. AI hallucination squatting. I love that term, slopsquatting.
It's so good.
It perfectly encapsulates the sloppiness of trusting an unverified suggestion and the maliciousness of squatting on that suggestion.
Slopsquatting is the most dangerous intersection of speed and security weakness. It relies not on a traditional software bug, but on a flaw that's inherent in the AI's training data and its confidence mechanism.
So the AI is trained on this massive historical corpus of code.
Right. And when you prompt it to perform a task, say, implement a new caching layer, it generates the most statistically probable sequence of tokens. Sometimes that sequence includes a reference to a package that should exist.
It sounds plausible.
Incredibly plausible, based on common naming conventions, project type, historical data patterns it has seen. But in reality, that package has either never been registered, or it's been misspelled, or it's an obscure name. This is the hallucination.
So the LLM is inadvertently providing a list of plausible but currently vacant targets for hackers to go and register.
Precisely. Let's walk through the exact prompt trap cycle that the source material details. It's a really clear sequence. Step 1. The developer prompts the AI. Maybe they say, I need to optimize how I handle rate limits for this external API, or I need a lightweight serializer for this specific data structure, something very routine.
And step 2 is the hallucination.
Yes. The LLM suggests a package name that sounds incredibly plausible, official, and efficient. It might suggest something like npm install cursor apaby optimizer lite, or pipey install fast serializer v2.
And it presents it with total confidence.
That's the key. It provides the exact executable command and presents this package name as a verifiable fact.
And this is where the hackers, who are now monitoring LLM output and common hallucination patterns, get involved. They aren't waiting for this to happen. They are anticipating it.
Exactly. This is the squatting part of Slopsquatting. Hackers anticipate common, generic, or plausibly named packages that an AI might invent, and they go register that exact package name on a public registry like NPM or PyPI.
And I assume they put just enough real-looking code in there to not look suspicious.
Often, yes. These malicious packages might contain just enough legitimate, non-functional code to pass a really superficial scan, but their true payload is hidden in an execution hook.
And that leads to step 3, the trap.
The trap. The developer, operating in that state of high-velocity vibe coding, trusts their agent. They simply copy and paste or just confirm the suggested install command.
They skip the human hesitation step.
Completely. They don't search the registry, they don't check the author, they just hit enter.
And step 4 is the punchline.
Immediate execution. The single installation command pulls the malicious package, and because these packages are designed to execute their payload immediately upon installation via those infamous post-install scripts, the supply chain is poisoned instantly.
And the recent cursor hack used this exact method.
To the letter, it weaponized developer trust to bypass all layers of human verification.
It's terrifying because it weaponizes the best part of the AI, its confidence and speed against the user. So Slopsquatting gets the malicious package into the environment. Now, how does Vector 2, Transitive Hell, turn that single infection into a systemic disaster?
Transitive dependency risk is the force multiplier, and it's what makes that 80-90 rule so terrifyingly real. The risk does not stop with the initial single malicious package you installed, like the Cursor API Optimizer Lite.
It just starts there.
It's just the entry point. Every modern package, even a tiny utility, relies on dozens, if not hundreds, of other packages to function. That single malicious package brings its own set of dependencies, and those dependencies, in turn, bring their dependency.
And so on and so on.
Exactly. So suddenly, a single npm install command, a single confirmation during vibe coding, can pull in hundreds, potentially thousands of unvetted, unscrutinized scripts onto your system.
And you have zero visibility into where all that code originated.
Zero. You don't know who wrote the developers of the developers or what exactly it is licensed to do.
So if the initial slop-squatted package is just a tiny Trojan horse, Transitive Hell is the entire Greek army rushing out into the city.
It's a perfect analogy. And this leads us to the ultimate supply chain compromise described in the source material, the severity of the cursor main.js attack.
Okay, what happened there?
This wasn't just about stealing data from an application. This was about compromising the developer's very workplace. This specific malware exploited the transitive nature of modern packaging to achieve something far more devastating than just stealing temporary keys.
What did it do?
It fundamentally modified the integrated development environment, the IDE itself.
So the editor I'm typing in.
The editor you are typing in. Since many modern editors and developer tools, including the targeted AI-driven IDEs, are built on frameworks like Electron.
Which is basically a web browser running a desktop app.
Right. It's all Node.js and JavaScript under the hood. The malwares was able to locate and overwrite the core startup file of the editor, typically the main.js file.
Wait, let me make sure I understand the gravity here. The tool I rely on to write code, the one I trust implicitly, is now compromised and actively working against me.
Exactly. The implication is profound. The attacker has turned the developer's factory floor into a weapon. It is the ultimate supply chain compromise.
What can it do once it has control of the IDE?
Anything. Once the core main.js is overwritten, the poison IDE gains persistent high-privilege access. It could potentially capture every keystroke you make.
Wow.
It could modify your source code before it's committed, injecting backdoors into other projects without you ever realizing it.
So it spreads laterally.
It spreads. It can steal credentials from your environment variables or any local files can access. It can simply exfiltrate data persistently, all while you, the developer, see the comforting, trusted interface of your editor running as normal.
So the breach is persistent, and the trust is fundamentally shattered.
Completely shattered. This level of operational compromise demonstrates that the idea of simply trusting the integrity of your development environment, because it's the environment you installed, is no longer viable. The malware is leveraging the speed of AI to inject itself into the highest privilege layer of the development stack.
And that means we cannot rely on manual checks or human caution anymore. The speed of the AI and the scale of transitive dependencies mean we need automated, systematic, and preventative defenses.
Precisely.
Here's where it gets really interesting. Because the solution isn't to slow down. We can't abandon AI velocity, and we certainly cannot manually eyeball thousands of lines of transitive dependencies across dozens of projects.
No, that's impossible.
The source material is clear. We cannot eyeball our way out of this. We need a specific automated toolchain, a defense stack, that takes the burden of skepticism away from the developer and embeds it into the infrastructure.
Right. And we have 5 critical tools to discuss that shift that security burden from human hesitation back to automated rigor.
And the key theme for all of these tools, as you implement them, is shifting left.
Exactly. We have to check things earlier in the process, ideally before they ever hit the developer's machine or repository, and certainly before they execute.
Let's start with the one tool that directly counters that instantaneous payload delivery problem. Tool 1, Pre-Installation Defense with socket.dev. Why does the timing of the defense matter so much in the age of fast installation?
The timing is everything because of those pesky post-install scripts we mentioned earlier. This is the critical weakness in the traditional software composition analysis, or SCA, model.
Okay, so what do traditional SCA tools do wrong?
Traditional security tools, the ones that look for known vulnerabilities, CVEs, they scan after the package has been fully downloaded and often after it has been fully built into the dependency tree.
So they scan during the CI/CD pipeline, or maybe when the package is just sitting passively in the node modules folder?
Exactly. And for malware, that timing is fundamentally too late. For the kind of malicious code in the Cursor API hack, the package executes its payload the very moment it is installed.
Right, through those post-install scripts.
Yes, the ones defined in the package's configuration file, like package.json. If your security scanner waits until the package is sitting still in the folder, the malicious script has already executed, stolen the critical.env file with your secrets, transmitted those secrets to the attacker, and potentially deleted itself or obfuscated its tracks. The crime is over before the detective shows up.
So waiting for a CVE to be filed is utterly useless against zero-day supply chain malware. Socket's unique approach, then, is that it operates as a behavioral analyst, not just a known bug database checker.
Precisely.
It looks for intent before the package is allowed to execute its intent.
Exactly. This is the shift from signature-based scanning to behavioral analysis. Socket doesn't just look for known vulnerabilities, though it does that too. It looks for behavioral red flags. It treats every package installation like a job interview and asks probing, suspicious questions about its intentions and its capabilities.
Give me an example of one of those questions.
Sure. Let's say an AI suggests installing a package that is a purely front-end UI component, maybe a calendar widget. That calendar widget should have absolutely no business trying to access the network during its installation process.
Not at all.
So Socket flags it. Does this package try to access the network? Or a package designed to transform CSS should not need to read critical system files outside of its own directory. Socket asks, does it try to access the file system outside of its designated sandbox?
And what about that fascinating indicator you mentioned, high-entropy strings? Why is that such a strong tell for supply chain malware?
High-entropy strings are a vital clue. Entropy, in this context, just means randomness. If a package contains long, seemingly random sequences of characters, obfuscated JavaScript, for example, it means the creator is deliberately trying to hide what the script is actually doing from human review and simple scanners.
So it's a sign of intentional obfuscation.
It's a huge red flag. Legitimate human-readable code tends to have low entropy. It uses readable variable names and common words. High-entropy code is a strong statistical indicator of malware trying to sneak past the guards. Socket flags this immediately as suspicious behavior, regardless of whether a CVE has been filed yet.
That is a critical advantage.
Yeah.
Let's bring it back to the vibe coding scenario.
Yeah.
The AI suggests that malicious Cursor API Optimizer Lite package. How does Socket specifically prevent the attack where other tools would fail?
It's the perfect defense layer for this exact scenario. If the AI suggests the installation, and that installation command is configured to pass through Socket first, the behavioral checks would instantly flag the package. Because a package that is supposed to be a light API optimizer has no legitimate reason to attempt to read the developer's home directory, or access network resources at install time, or look for files named .env or .shiderdors.
So it sees the suspicious behavior and just blocks it.
It stops the malicious package before that crucial post-install script even has a chance to run. It neutralizes the immediate risk inherent in that blindingly fast, automated installation suggested by the AI.
That makes Socket the essential layer 0 defense, the necessary human hesitation replacement. But if code gets past that initial behavioral check, we need tools that maintain the health of the codebase long-term and manage the sheer volume of alerts.
Exactly. If Socket stops the initial break-in, our next tool is about making sure the interior of the house stays clean and the guards don't get exhausted from false alarms.
Which brings us to tool 2, the Zen firewall with Aikido.dev. Aikido is mentioned in the sources as addressing noise. This feels like a soft issue, but in reality, developer burnout from irrelevant security alerts is a massive security problem itself, right?
It's absolutely mission critical. Noise means false positive security alerts that are either non-exploitable, low priority, or just plain wrong.
And when security tools generate hundreds of these alerts every day,
Developers develop alert fatigue. They start ignoring the warnings, which means when a real critical threat comes through, it gets lost in the flood. Alert fatigue kills developer velocity and creates massive security gaps.
so Aikido is praised precisely because it reduces this noise.
Right, it aims to be the Zen firewall, focusing only on actionable threats that are actually reachable in your code.
And it's an integrated platform.
Another huge advantage, Aikido combines code scanning or static analysis, cloud posture management, and supply chain security into one consolidated dashboard. In an AI-driven environment, this integration is vital.
Why is that?
Because the AI isn't just writing application code, it's often generating infrastructure as code or pulling dependencies that affect the cloud layer. You need a unified view to see the whole picture.
So how does Aikido act as a guardrail in this high-velocity vibe coding environment?
It's all about preventing contamination before the code hits the main repository. The vibe coder moves fast. The AI generates code, and that code might do one of two things.
Okay.
One, it could pull dependencies that, while not immediately malicious like the post-install script stuff, contain known high-risk vulnerabilities.
And 2,
Two, the AI accidentally generates code that exposes hard-coded secrets, API keys, database passwords, tokens that are about to be pushed up to your Git repository.
I see. So the speed of generation means the human supervision is delayed, and Aikido catches the mistake right there in the generated file before it gets committed.
That's right. The Zen firewall detects if an AI-introduced dependency brings in a critical known vulnerability or if the generated code contains secrets. It throws up an instant, high-confidence warning directly in the developer's workflow or as a check on their pull request.
So it prevents the developer from polluting their own repositories. Yeah.
Exactly. It stops them from adding vulnerable code or leaked credentials that originated from an overly helpful but security-blind AI agent. It ensures that the speed of vibe coding doesn't translate into security debt that lasts for years.
This sounds like a great triage and hygiene system, but it still relies on checking the contents of the code. We still haven't solved the core identity crisis. How do we know who actually wrote that code in the first place?
A critical question.
That's where we move to tool 3, focusing entirely on identity and provenance. As the source asks, who wrote this code? Did it come from the official team or just some random person named CursorFan 2025 on a public registry? We need cryptographic proof of origin.
Identity and provenance are the most fundamental long-term defense against the entire hallucination squatting and typo squatting problem. When the developer trusts the AI, they stop checking the identity of the package publisher.
So we have to replace that human skepticism with cryptographic certainty.
That's the mission of Sigstore. It's a crucial open-source project designed to provide tamper-proof provenance for all software artifacts. It's essentially creating a digital chain of custody for every single piece of software.
How does Sigstore actually create this verifiable identity and chain of custody? What's the mechanism?
The mechanism is both clever and reliant on existing internet standards. Sigstore allows developers to cryptographically sign their code artifacts, their containers, binaries, or libraries, using their standard OpenID Connect or OIDC identity.
So that's what I use when I log into a service using my Google or GitHub account.
Exactly. When the developer signs the artifact, Sigstore uses a short-lived key tied to that specific login event. This signature and a verifiable record of who logged in and when they signed it is recorded in a public, transparent, append-only log.
A transparency log.
Think of it like a notary public for the software world, witnessed publicly by everyone.
And that's where cosign comes in. It reads that notarized log.
Cosign is the enforcement and verification tool. Before you pull a critical binary or container image into your environment, for instance, to deploy it to production or use it in a build process, you use cosign to verify that public signature against the transparency log.
And what happens if it doesn't match?
If the signature doesn't match the one that's logged, or if the code artifact has been tampered with since it was signed, cosign blocks the process immediately. It enforces that required chain of custody.
So, applying this back to our crisis, if the malicious Slopsquatted cursor API package isn't signed by the official cursor organization, or if our corporate policy mandates that all packages must be signed by a trusted vendor.
Cosign acts as the gatekeeper. It moves trust away from the plausibility of the package name, which the AI has failed at, and toward cryptographic proof of origin.
So even if the AI suggests the package, and even if Socket didn't catch the behavior, cosign checks the ID card.
That's a great way to put it. If the package doesn't have a valid ID card signed by a recognized authority, it doesn't get deployed or installed. This is also critical for preventing sophisticated attacks where a legitimate package is compromised, because any change to the package invalidates the original signature.
This sounds incredibly complex to implement across a large enterprise. How do developers maintain velocity if they have to ensure every tiny dependency they use has been properly signed via Sigstore?
That's the implementation challenge, and you're right to point it out. You don't try to sign every single transitive dependency from the start. That would be impossible.
So where do you begin?
You focus on signing the artifacts you produce and enforcing signing checks on the most critical, top-level, internal, or vendor-supplied dependencies. The security benefit comes from mandating that your own tools, the IDE, the build system, the core frameworks, must be signed.
And for third-party packages?
For third-party packages, you rely on the community adoption of Sigstore, which is accelerating rapidly. It's a monumental shift, but a necessary one to move beyond the current state of blind trust.
That makes sense. We've covered behavior, hygiene, and identity. Now we move to visibility. Even if the code is signed and safe, the sheer volume of code pulled in by vibe coding leads to the next problem: blindness.
Right. You can't protect what you can't see.
Which brings us to Tool 4, the ingredients list with SBA, using Sift and CycloneDX. The source notes that AI agents are notoriously bad at documentation. They add libraries, use snippets, and forget them instantly.
This is a matter of basic inventory control, a necessity since the U.S. government mandated SBOMs for software sold to federal agencies. If you run any kind of complex manufacturing, you need a meticulous list of every component, every nut, bolt, and wire that goes into your final product.
And in software, that is the Software Bill of Materials, or SBOM.
An SBOM is a formal, machine-readable inventory of every library, module, dependency, and snippet, including their licenses, versions, and internal components used in your software. It is the definitive ingredients list generated at build time.
And we have two key components for implementing this: Sift and the CycloneDX standard.
Yes. Sift is the open source tool used for generation. It's designed to be incredibly fast and comprehensive. It can analyze a project directory, a container image, or a file system, and automatically generate that detailed manifest.
So it doesn't rely on the developer manually updating a manifest file?
No, it scans what's actually there. And CycloneDX is the industry standard format, an extremely detailed JSON or XML schema for how that information is structured.
And why is the standard format so important?
Using a standard machine-readable format is crucial because it means the SBOM can be easily consumed and queried by all the other security tools in your defense, stack your vulnerability scanners, your inventory management systems, and your governance tools. It creates a common language.
So how does this help the vibe coder deal with the fundamental problem of transitive hell and forgotten code?
It provides instant organizational querying. That is the true power. Let's go back to our compromise scenario. Imagine 6 months from now, a 0-day vulnerability is discovered in one specific, deep, transitive dependency. Say, a utility nested 5 layers deep within that original cursor epi optimizer lead that the AI pulled in.
Okay, so a log4j style event.
Exactly. In the old world, a security team would have to scramble, send out emails, and hope every developer documented the recent AI imports and knows which deep dependencies they pulled in. It's chaos.
It's a fire drill.
With an automated SBOM generated by Sift and stored in CycloneDX format, the security team can instantly query their central SBOM repository and ask with absolute certainty, are we using version 1.2.3 of the vulnerable utility anywhere in any project across any team?
It is surgically precise.
It ensures visibility and accountability. Even if the human developer forgot the AI added the code, and even if the AI didn't document it, the security team knows exactly where that risk lives. This allows for surgical remediation, a patch, an upgrade, or removal instead of a frantic organizational fire drill. It turns weeks of searching into seconds of database querying.
That brings us to our final defense layer. We've stopped the bad behavior, checked the identity, and created a definitive list of ingredients. Now we need the final, non-negotiable wall.
The policy layer.
This is Tool 5, Policy Enforcement with OPA, the Open Policy Agent. This feels like the strongest line of defense against the fundamental failure of AI trust. It's the shift in mentality from passively asking, "Is this safe?" to actively saying, "This is not allowed."
That mental shift is the culmination of all our previous steps. OPA, often utilized with gatekeepers in Kubernetes environments, allows organizations to write detailed executable security policies as code. This is a crucial evolution from having static rulebooks that nobody reads.
Policy is code.
Exactly. You write your security policy in a high-level declarative language called REGO. These policies are then executed automatically across your entire infrastructure, from source code checks to CI/CD gates to runtime environments.
So instead of relying on a human to remember a rule or relying on an AI not to hallucinate a bad package name, you write the rule into the OPA engine.
And if any action violates that rule, the action is blocked hard and fast. It's security defined by the organization, not by the latest vulnerability report. The organization dictates the acceptable boundary.
Let's get into the mechanics. What kind of specific policy rules can we use with OPA to block the kind of AI-driven vulnerabilities we've been discussing, particularly Slopsquatting? Give me a practical example.
The source gives us examples that are phenomenal counters to the AI trust problem. Let's start with package origin. We can write a REGO policy that enforces no packages allowed from unverified namespaces.
What does that mean in practice?
The REGO code would check the proposed dependency name and block the installation if the package registry path doesn't match a predefined whitelist of approved vendors or internal package repositories. This is critical. If your company uses a private registry or only trusts packages from namespaces owned by 10 approved vendors, OPA enforces that policy universally.
So if the AI suggests a plausible but unverified package from a random user.
The Slopsquatter's product, OPA blocks the install immediately.
And the second example targets the speed of malware deployment itself.
Yes, no packages allowed that are less than 30 days old. This is a powerful time-based offense. Hackers register malicious packages, often typo squats, and deploy them instantly, hoping to catch the first round of automated installs.
So you're creating a mandatory quarantine period.
You are. By setting a minimum age, say 30 days, you block brand new, unvetted modules. This gives the community, public scanners, and behavioral analysts like Socket time to identify and flag the malicious packages before they can ever enter your trusted environment.
This truly feels like the ultimate anti-hallucination shield because it neutralizes the risk, regardless of the LLM's confidence.
It does. It provides an absolute boundary. It neutralizes the risk of an AI agent pulling in a typo-squatted library by preventing the installation of any package that hasn't been manually whitelisted or verified against those defined organizational policies. This ensures that even in the rush of vibe coding, the enterprise retains absolute control over the code allowed into the environment.
I have to play devil's advocate here. If OPA is policy as code, doesn't that just replace the human hesitation bottleneck with a new rigidity bottleneck? How do development teams maintain velocity if they have to manage a complex redo policy rulebook and every new dependency requires a manual whitelist addition?
That's the core tension, and it's why OPA needs to be implemented strategically. The policies shouldn't be overly broad. You use them primarily to enforce foundational security tenets.
So you don't block everything.
Not at all. For example, the 30-day rule can have exceptions for approved vendors. The goal isn't to block everything, it's to force a moment of automated scrutiny only where the risk is highest. The superiority of policy as code is that once the rule is written, it's enforced automatically and consistently everywhere, far more reliably than any human could.
So the friction shifts.
The friction shifts from manual review for every component to governance review for new policy rules. Once the governance rules are set, the development velocity underneath that framework is actually faster because developers aren't wasting time manually vetting packages that are fundamentally disallowed anyway.
That is a phenomenal tool stack, covering everything from pre-execution behavior to identity to organizational policy. But as we know, tools are only as good as the strategy behind them. The source material emphasizes that we need a golden path for the AI.
Absolutely. The tools are the defenses, but the golden path is the battle plan. We have established that the speed and autonomy of the AI agent are the vulnerability. To truly secure the vibe coding workflow, organizations must define a golden path.
Which is a pre-approved, vetted set of tools, libraries, and processes.
Exactly. It's a set of tools and libraries that AI agents are explicitly instructed and often constrained to use. This strategy moves the organization from reactive security scanning waiting for a breach to proactive security architecture.
So it tells the AI, you can move at lightning speed, but only within this secure corridor.
That's the idea.
So what are the specific, non-negotiable strategic actions we need to take to solidify this path?
We need 3 specific actions. First and simplest, pin dependencies. This must be a non-negotiable organizational discipline for AI and human coders alike.
Never use latest.
Never allow an AI agent to write just latest or a broad version range like 2.1 or 3.0 in configuration files like package.json or requirements.txt. That latest tag means the application could pull in a new, unvetted version, potentially malicious on every single build. This is how silent backdoors can propagate.
So you always pin to a specific hash-verified version.
Always. If the package changes, even by a single character, the cryptographic hash changes, and the build fails, alerting the team to potential tampering or unforeseen, unvetted updates. It ensures that once a package has been vetted and signed, the exact same code is used every time, unless explicitly updated through a formal review process.
It locks down the supply chain.
Precisely. The second major action, and perhaps the single most effective choke point, is implementing a private registry proxy. This is a mandatory gateway for all external code.
So you use a tool like Artifactory or Sonatec Nexus?
Yes, or a similar solution to proxy public package registries like NPM, PyPI, and Docker Hub. You block your developers and your build system from having direct, uncontrolled access to the public internet's chaotic ocean of packages.
So everything has to pass through your internal organizational gate, no exceptions.
That's the policy. Packages are only allowed into your internal proxy after they have passed a mandatory internal scanning and policy check. This includes behavioral checks with Socket, vulnerability checks, and policy enforcement with OPA.
So if an AI hallucinates a name, or if a human makes a mistake,
The request to download it from the public internet hits a wall. The proxy scans it for malicious behavior before it ever enters the developer environment. Once it passes, it's cached in the proxy, becoming a trusted source of truth for all internal dependencies. This is how you reclaim control over that 90% iceberg.
and the final action is about restoring that crucial human element, but channeling it correctly.
The final and perhaps most challenging action is the human review mandate. The vibe must end at the pull request stage.
So you can't completely outsource security responsibility.
You can't. While the AI increases velocity by 10x, the human must retain the final critical check. The code diff must be reviewed not just for logic, function, and style, but specifically for provenance. We need to institutionalize this skepticism that the AI eliminates.
So we make the first question on every code review a simple check. Where did this import come from, and is it pinned and approved?
It must be institutionally enforced. That simple question forces the developer to verify the source, confirm the signing status, and ensure the package was pulled from the trusted internal proxy. It restores the human hesitation filter at the most critical choke point in the entire development process, the gateway into the main code base. Without this final check, the entire automated defense stack is undermined by a single merged pull request.
This has been a critical, foundational deep dive. We started by defining the crisis vibe coding, bypassing the crucial human hesitation filter, thereby accelerating the deployment of malware into a massive, unseen iceberg of third-party code. We traced the specific modern attack sectors: Slopsquatting, which weaponizes AI hallucinations for instant payload delivery, and transitive hell, which resulted in the ultimate supply chain compromise when the IDE factory floor itself was poisoned.
Right, the problem is clear.
But we didn't stop at the problem. We've outlined a powerful, multi-layered defense stack necessary to bring rigor back to the velocity AI provides.
Layer 1, behavioral analysis and pre-execution defense with Socket.
Layer 2, integrated security and noise reduction with the Zen firewall of Aikido.
Layer 3, cryptographic identity and chain of custody with Sigstore and Cosign.
Layer 4, mandatory visibility via machine-readable SBOMs generated by SIFT and governed by Cyclone DX.
And finally, Layer 5, active policy as code enforcement with OPA.
The conclusion from the source material is stark, yet empowering.
It is. The Cursor API hacks demonstrate that the software supply chain is the softest target in the age of accelerated AI coding. The speed of vibe coding is undeniably seductive, but it must be meticulously paired with the rigor of supply chain defense.
The era of blind trust in simply running npm install because an AI suggested it is conclusively over.
It's over. And by strategically implementing these defenses pinning dependencies, mandating a private proxy for all external packages, and mandating provenance checks at the pull request level, organizations can build a resilient fortress around their workflow.
This ensures that the only code running on their machines, and ultimately in their production environment, is code they have explicitly verified, either cryptographically or structurally.
The final challenge, the new normal we must embrace to harness the power of AI safely, is simple, non-technical, and profoundly necessary.
We must relentlessly verify the vibe.